Now, I've got some announcements to be made. Two things right off the bat. We have a new position, and that's when you go to the meetings now at Perkins. When you go in, you're going to be greeted by Joe Stark. And Joe is going to be our new official greeter. And he's going to greet the people as they come in, and he's going to ask you to sign the registration, or at least print the registration so we can read it. And also, if you have any information that's changed in, say, the past year or whatever, that you can put down that new information, phone number, email, whatever it is, that we can try to keep that up to date. And then he's also going to be greeting any guests that come in and try to find out a little bit about them, get their name, and he'll be later on introducing them to the group. And if they choose to do so, maybe give them a minute or two to speak and say who they are. Okay. Don's not here at all, is he? I didn't see him. Brad, would you like to do your report on JCAP? Anything that you have to say there?
Sure. The John Glenn Astronomy Park is currently open for anybody to go and observe from. We have a lovely plaza with power and such, and if you'd like to brave the cold and go down there, we do not object to that. So please feel free to do so. Our programs will start back up. Our official weekend programs will start back up in March, on the weekend of March 4th. Those are, of course, weather permitting. Occasionally, I will announce a program if it is an exceptionally clear night and the conditions are right, and it's a nice Friday or Saturday. But yes, if you'd like to go down there, please feel free. So, and that's all I have to say.
Okay, Dana, I believe Dana Grubb had a message here she wanted to give.
Right. I wanted to extend an invitation from the Kalamazoo Astronomy group that they are having a free online introduction to astronomy course. If you look in the chat window, I put a link where you can register, and the dates of the class, they're taught on Saturdays from 1 to 3, 5 Saturdays.
Okay. I guess there's no other messages then, and
I need to say something about CASIS.
yeah. I was just looking to see though if Don came in though yet. So yes, I do have you down here. And
Okay.
Isaac, if you would want to give your report on CASIS.
Well, good evening, everyone. Not only am I the speaker, but I'm also the director for CASIS, the Columbus Astronomical Society Imaging SIG. We normally have meetings on the Saturday past this meeting, on the third Saturday of the month. So, but because of the intro to astronomy class from the Kalamazoo Astronomy Society, I'm going to take that class, and it happens at the same time that we would have our CASIS meeting. So, for the foreseeable, it looks like that this month and next month, it looks like we're going to be having it on the third Saturday of the month. So that will be on the 22nd. I will make the official announcement. But if you're interested on taking images of the cosmos and learning how to do it, and also learning how to process it, one of the things that I'm planning to do is that starting on January, we're going to be talking about processing, image processing software for imaging. So if you're interested in that, definitely plan to come over to the meeting again on the 22nd. That's all. Thank you.
Okay. And Don definitely did not is not here. Oh, well, that's Don Leonard, but that's our VP there. But I was looking for Don Stevens here, but I guess he isn't here. So, okay, I guess we'll go ahead and get going with our program.
Can I point out something?
Sure.
That is the fourth Saturday, Isaac, not the third.
Oh, you,
Hey, Isaac, you're on mute.
yeah. Isaac?
Yeah.
You're on mute.
Okay, thank you. I appreciate that. So it is I did say February 22nd, it's the 26th, right? That's not true.
The 22nd is the fourth Saturday, and it would be 1 week later than usual.
I'm looking at the wrong month. That's what happened.
Well, the 22nd is the fourth Saturday of January.
Right. And the third Saturday is the 15th, right?
And I think that's when the CAS program starts, right?
Correct.
Yes. So we'll have it on the 22nd at 12:30. So that will be the next CASIS meeting where we'll be discussing the image processing software and how to use it. So so yeah, that's 1, 2, 3, the fourth one. That is correct. So that will be the fourth Saturday of the month. Thank you.
Okay, I think we're all set. And our speaker tonight is Isaac Cruz, and he'll be doing his presentation on locating exoplanets. Isaac?
Thank you very much, Jim. I appreciate. Welcome, everyone. And I'm Isaac Cruz from the Columbus Astronomical Society. And I'm going to share the screen so you all can see what I'm talking about. Please let me know if you don't see the first slide. All right. And I want to welcome everyone, to this meeting. I think that we're hoping for at least getting to be together one of these days, and we'll do what we can to actually keep on in our endeavor for more astronomical knowledge. So with that, let me start with a little bit of an interesting fact. In the year 1600, we had a gentleman that basically promoted the idea that there were planets around all the stars. And basically at that time, he paid with his life. He was actually burned at the stake by the Roman Inquisition. And that was only 422 years ago. Yeah. And it's really quite amazing, right? I mean, we are in a situation where we're very lucky. Science basically continues to go forward, and it gives us the opportunity to actually make discoveries and see beyond what we normally would be able to see. And right now we have close to 5,000 exoplanets that have been discovered. So in that respect, is something that is quite amazing. We have satellites that have contributed tremendously to that to that number of exoplanets that we know up to now. And we'll be talking a little bit about not only the current status of the science, but also basically how you can do it yourself. Okay, I mean to to actually know how you can actually do that. So we'll define, what an exoplanet is and some of the terminology that is associated with, with basically locating exoplanets and measuring, how you actually know that it's actually an exoplanet. We'll of course define the, what exoplanets are and give a little bit more information on what, the current status of the science. And then I'll talk a little bit about, what are the challenges that if you as a astronomer, citizen, scientist, you want to actually contribute to the body of knowledge on exoplanets, what are the challenges that you actually face to detect exoplanets from here, from Ohio or from anywhere that you are. And as such, I'll give you a methodology, a step-by-step of what do you need to do to actually be successful in actually getting your first exoplanet, and then show you, the results, what the data looks like after everything is compiled and analyzed. And I'll finish with resources. It's just one slide, and I'll have to tell you that at the end of the meeting, I'll put a copy of the links of the resources that I've been talking about, that I'll be talking about throughout the presentation in our listserv for you folks to actually use if you so desire. So let's start with definition, right? First of all, let me start with an eclipsing binary. An eclipsing binary is just like it says over there, two stars that orbit each other, as you can see in the animation in there. The orbital plane is in the same line of sight to Earth, and then it produces mutual eclipses. And as you can see in the animation, the light intensity of that star varies with as the other star actually goes in front of it. So one thing that is important here is that eclipsing binaries are relatively simple to detect, mainly because the decrease in brightness of the host star, of the main star, actually varies by about 1 magnitude. So that actually is quite a lot, right? Exoplanets is an extra solar planet, a planet beyond our solar system. So any planet that orbits a star that is not our sun is an exoplanet. And as I mentioned before, we actually have close to 5,000 exoplanets that have been discovered already using current technology. The host star is the star that the exoplanet orbits, right? So we call that the host star. And a transit is an event where a celestial body, it doesn't matter what it is, celestial body seems to pass across the face of another celestial body. And an example is on the second animation over there in the lower left-hand side, where you actually see Venus actually transiting the face of our sun, right? So that was on the last transit. So that's a transit, right? So a little bit of history about exoplanets. The first confirmed exoplanets, right? I mean, so we actually didn't know that for sure. There were actually planets orbiting other stars. In 1992, using the Arecibo radio telescope in Puerto Rico, and yes, that's the one that got destroyed a couple of years ago, unfortunately, was analyzing a pulsar, and in 1992, it actually confirmed that there was a planet that was orbiting that star. In 1995, the first exoplanet around a sun-like star was discovered. That was 51 Pegasi, and you see that it says 51 Pegasi b, like in Bravo. The terminology for exoplanets is that the first exoplanet that is discovered and is typically the closest one to the host star is designated as the B, like planet B. If there's another one, it would be C, and so on and so forth for multiple planets, for multiple exoplanets. Okay. Between 2006 and 2012, CODOT is a French-based satellite that was sent out, and their mission was to actually look for exoplanets. And there's a lot of data that actually has been used to actually to try to find exoplanets. And so they have contributed to the number. Of course, probably you're more familiar with the Kepler mission that in between 2009 and 2018 focused on a patch of sky of the constellation of Cygnus, the Swan. And they have been, for sure, the most prolific detections of exoplanets, with more than 2,000 confirmed detections altogether. The Kepler main mission ended in 2013, but then got extended for 5 more years, and they call that second light, or K2, and they continued to contribute. They continue to contribute to the experiments and, of course, the detections through 2018. And then in 2018, we had tests, and there's quite a lot amount of data. TESS stands for Transiting Exoplanet Survey Satellite, right? So the good thing about satellites, right, of course, is that you do not have to fight the atmosphere, right? I mean, to basically away from that, and it makes it very good. TESS also have thousands of, like 1,000 of the of exoplanet detection as well. And to date, like I said, we have about 4,900 exoplanets have been discovered. And most of them, I mean, hundreds, are circling a 13th magnitude star or brighter, right? So how are these, let's find out here, how are these exoplanets being discovered? So there's, I say 5 ways of detecting an exoplanet. I should amend that to say the 5 most popular ways of detecting exoplanets. There's probably about 3 or 4 more, but basically the most popular ones is the photometry that detect minute changes in magnitude of the close to 5,000, 3,000, 3,400, and some have been detected using photometry. That makes it 75% of the exoplanets that have been detected are actually using photometry. Radial velocity detects variations on the speed the host star moves toward or away from Earth, and 908 have been detected using that. Gravitational microlensing is also a way of detecting exoplanets. 121 exoplanets have been detected using that. Direct imaging, right? I mean, the past 3 that I have talked about, the majority of them is an indirect way of detecting an exoplanet. As you can see, we have not talked about being able to take an image. So out of the close to 5,057 have been imaged directly. So that's kind of neat. Astrometry detects minute changes in position caused by gravitational interaction. So if the radial velocity is, this is basically a byproduct of the radial velocity, depending on the mass, the relative mass of the two bodies, it may change the position of the star in the sky enough to be able to detect that change. Only 2 of the exoplanets have been detected using this method, right? So, as I said before, photometry is the most popular one of that has been used to actually do that, and is the one most commonly available to the amateur astronomer, especially for the non-professional amateur astronomer or professional astronomer that doesn't have access to to instrumentation in the satellites, right? So, but for us, for the amateur astronomer, the photometry is the way to go for us to be able to actually look at that, right? So what I would like to do is kind of give you a little bit of a illustration on this exoplanet detection and what does it actually mean, right? So, like I said, 3,461 planets have been detected using photometry. So you actually have a planet that is circling a star. If the orbit actually passes that we can actually see it. Well, if we measure the light that actually comes from that star, we'll see a dip that you can see on the left-hand side on that illustration. So that is the basic principle of photometry detection, right? So one of the neat things about that is that if the if the planet is big, it's large, then obviously it will occlude more of the star. So at that point, you'll have a deeper dip, if you will, on the brightness of that star. And if the planet is relatively smaller, then you'll actually have a smaller dip, or the light curve will have a smaller dip. And that's how we know how we can actually compare the the sizes of these planets that are orbiting this star. So this as we go along. So how do we detect multiple planets? Well, you will see, right, if you actually have a system that have multiple planets, it is exactly what you might expect. We'll see a different reduction in the light curve, for one planet, and then if you keep on looking, you'll see reductions for the other planets, and that type of interaction is actually shown in the light curve itself. So using this methodology, you can see that we can detect not only the actual exoplanet itself, but the number of exoplanets, and then the relative size of the planets themselves. Now, as far as the radial velocity, remember, this is the second most popular way of detecting an exoplanet. Well, it has to do with how much does the star actually, it seems to be moving toward or away from us, right? So if as the star moves away from us, it actually shifts on the red, and then as the star moves toward us, it actually shifts on that on the blue. And basically that wobble, right, that radial velocity change is, can be measured, and again, based on that, we can actually tell that there's a planet, an exoplanet. Most of these, the mass has to be the relative mass of the planet actually has to be large enough to create that, right? So most, if not all of these 908 exoplanets that are associated with the radial velocity method are, massive planets that basically, again, interact with the star to show us that. Gravitational microlensing is an interesting way. Basically, if there is a massive like galaxy behind the transiting exoplanet system, then what we will see is that basically you see a little blip on the lower right hand corner in there. You'll actually be able to actually see that in there. So let me show you that. You're looking basically at a small change on the a background galaxy, something that is very massive, and then that actually basically gives us an indication that there is a that there's actually in there an exoplanet. For direct imaging, you actually need to be able to basically use a coronagraph, something that you'll be able to cover the main image of the host star, and then the exoplanet actually shows up. As you can imagine, the brightness of the star is thousands of times brighter than the brightness of the planet. So in that respect, we have to use something that covers the star, and then the exoplanet appears in there. So 57 of these we've been able to successfully use this method to be able to see exoplanets. And astrometry, right? I mean, finally, this is a really massive system where the star basically location, the position in the sky relative to other stars changes enough that we are able to detect the difference, and based on that also wobble, right? And based on that different position and movement, we can not only determine that there is an exoplanet, but also the mass, right? So, and again, this also is related to massive exoplanets, facing a host star. Only two of these, only two exoplanets have been recorded using this method. Okay, so at least what kind of the method, what type of methods can be used to actually use this. And again, in our case, we have to remember that photometry is for us the most what is most available to the amateur astronomer. So as I mentioned before, exoplanet detection requires very precise measurements of brightness. Typically the star brightness reduction is about 1%, between 1 and 2%. You will see as we go along that that is what the brightness reduction is all about. In comparison to the eclipsing binary, which I already mentioned, brightness reduction is about one magnitude, right? So let me give you an example of what an eclipsing binary it's all about, right? So an eclipsing binary light curve, I did this in 2007. Basically, I tried to look at a well-known eclipsing binary in the Hercules constellation. This is SZ Herculi, and the information that allow me to take all this data is available in the AFSO website, the American Association for Variable Star, and if you're interested in actually looking for variable stars, you basically would have to get familiar with AFSO. What you can see here is you see this horizontal lines that actually are labeled reference start light curves. That is the light curves. That is the brightness of stars that obviously don't vary, right? I mean, you basically they're stayed steady throughout the 2 or 3 hours that I actually was out taking images for this star. And then you can see the eclipsing binary curve that basically goes from close to 10 all the way down to 11 as far as magnitude is concerned. And as the time goes by, basically as the star is eclipsed by another star, and you can see the very, very marked and very obvious dip in star brightness in this curve, right? Now, in fact, you can actually tell eclipsing binaries. You can actually tell a 1 magnitude difference. So you can even tell this if you're an experienced person that actually looks at variable stars. You can actually see this basically with your naked eye or with telescope, with binoculars, and it's kind of amazing. But the reason why I'm showing you this is because if you're interested in detecting, in finding and recording exoplanets, you need to be familiar with the process of taking these curves, of generating these curves, which is every one of those little squares in there is an image, and basically you have to analyze it to with software to basically get the information that you're actually getting here. So if you're interested in actually getting into detecting exoplanets, I would recommend that you do this first and get familiar with the process, and get yourself very very comfortable in actually doing this many times. And again, this is something that is very, very reachable by every amateur astronomer that actually wants to do this. So the other challenge that is associated with exoplanet detection is that the transit, the planet doesn't go across the host star very fast. So transit typically take hours, which means that if you're going to take images during the transit, the weather needs to stay clear for a long time, right? You're going to be taking hundreds of images to be able to detect these minute changes, and it's a little bit hard to plan. That's the reason why I say that if you want to get into the actual process of imaging, of detecting the exoplanets, you need to do eclipsing binaries first, because that actually helps tremendously. But despite all these challenges that we had just talked about, it can be done. It's it's something that with some perseverance, it definitely can be done. So with that, let me give you a little bit of how you, as an amateur astronomer, can be successful in detecting an exoplanet. So first of all, you have to find out, okay, if I'm going to detect an exoplanet, I need to find out where in the sky do I point my telescope. And the number one database for where the current exoplanets are and the repository for everything that has been discovered is the NASA Exoplanet Archive. And there's that link in there, which is caltech.edu. And again, don't worry about making notes of this. I'll be putting them. I'll be putting them in the listserv as we go along. Once we're finished with the lecture. So there's also the Czech Astronomical Society Exoplanet Transit Database. This is actually from amazingly enough, is the Czech Astronomical Unit, Astronomical Society. So another CAS, and they have taken the data that they can find publicly in the internet and made their own database. Love them for that. I mean, I think that actually says a lot, and it has sometimes a little bit more information arranged differently. It's the same information, but it's arranged differently from what Caltech actually provide. So this is kind of neat. If you go to the Exoplanet Archive, the NASA Exoplanet Archive, which again is in caltech.edu, it's a site on caltech.edu, you'll see that there are, information related to TESS, Kepler, K2, KELT, and UK IRT. TESS, which is, as I said, the Transiting Exoplanet Survey Satellite, there's still 1,385 exoplanets that need to be analyzed and really discovered. Basically, they need to be analyzed and see if they're truly exoplanets, right? So what does that mean? That means that there's opportunity for us as amateur astronomers to again help on the adding to the body of knowledge of men in regards to exoplanet. There are 2,366 potential exoplanets from the Kepler's first mission. So the one that the little tab over there, you can see that says Kepler. There's about close to 2,400 in there, and then from K2, the second light, there's about 890 potential exoplanets. So I'm telling you this because basically what we have here, right, is an opportunity. It's an opportunity for us as amateur astronomers to actually, again, do some science, do some really, really neat science. Okay, so when you actually go to that site, basically, how do you find your targets of interest, right? You will see that it actually has three different choices. You have the transit surveys that I just showed, tools and services, and work with data, right? So what you need to do is you take project candidates, and when that's basically what you want to look for, right? I mean, these are the ones that you want to analyze. Well, and then you go to transit and ephemeris service. The transit and ephemeris service, I mean, it's kind of funny because it says predicted observables for exoplanet service on the upper right hand corner. And what happens with that is that those predictable observables do not allow you to put any location on Earth. In other words, where is your observatory? So to be able to select from Earth, you're going to be trying to do your analysis, your detection. You have to go to Transit and Ephemeris Service, which is highlighted there. And when you click that button, you'll end up with a form that you have to fill up that basically has the transiting planets, right? Now, in this case, this example that I'm giving you, let's look. We're looking for a confirmed planet, which I suggest that you actually do first, so you can actually get an idea on, what do you have to do to be able to get to detect an exoplanet. And you can see that I selected over there confirmed planets and transiting planets. On the second line, you'll actually see that it says Kepler object of interest, and there's candidates in there. You can select that, and K2 candidates is there as well. But in this case, we are looking for a transiting planet that is confirmed. And then you tell it on the lower right-hand corner where the location of your observatory. In this case, this is Hutville, which is 40 and minus 82. That's Central Ohio right there. And we say predict events. It takes a while to actually create the prediction, right? It creates the ephemerides for all of these. When I did this, the original research that I did showed 8,657 of these transiting exoplanets, things that can be seen. However, what is important to look for in here, right, is again that it will occur at night. So it will occur for your location at night, and at a time that you can actually look at. And then I'm going to show you, I don't know if you guys can see my cursor, but kind of in the middle, there is this transit depth calculated %. You see a bunch of them are 0.0s and 0.0046. You're looking for something between 1 and 3%. Anything that is less than 1%, you will not be able to detect terrestrially. It is very, very, very hard. So in this case, the transit depth for the star that I wanted to look at is 2.23. The star is HD 189733, and the exoplanets is HD 189733b. That's the first exoplanet out of that star, right? So, and it tells me, the array and deck, which is needed for you to be able to point your telescope at that star. And you can see that the target observability, this was in February, it's actually during the night. So basically we'll actually try to use this as something that we'll be able to detect altogether. So it's kind of funny, right? I mean, 189733, if you look, it's a relatively close star. It's only 63 light years away from us. It's in the constellation of Vulpecula, and it's really amazingly close to the Dumbbell Nebula, or M27. So it's just west of it, and is relatively bright star. It's actually magnitude 7.6 if I'm completely good at this. And I said, okay, that looks like a target that I can try to go for, and try to look at, right? So To be able to do this, we have determined when the transit will occur. So we know when we need to set up. So we need to generate an observing plan. We need to record the location and magnitude of the host star. And as we said, is close to M27. We'll find out how we found that out. We need to note the ingress, mid-transit, and egress times. That's provided by the database in Caltech. Once you do the search, you actually be able to see those times. You determine the elevation of the host star, right? I mean, so you want to actually have ideally more than 30 degrees. 30 degrees above the horizon is 2 atmospheres. So the less air you have to go through, the more, the better you are. And you have to choose comparison stars, because I mean, as we talked about before, you need to be able to compare the dip, how little that star actually diminishes as far as the brightness of that star is concerned. Then decide which filters to use. I use a visual filter, also known a V filter for this. You determine exposure time and number of exposures. We'll talk a little bit about that, and also the optimal camera angle if you want to basically rotate the camera to get different comparison stars and so forth. If you're able to do it, then you can determine that, right? So most of this, right? I mean, we talked about that the ingress, mid-transit, and egress times. Those times are provided by the search that you just did, the day that you're going to be doing it. But everything else, you'll need a good planetarium program, that has the database that includes all those, the star that you're going to be looking at. In my case, I use the SkyX, but Stellarium actually has a fantastic database of stars. CardDCL, which is also free, also contains a very good catalog of stars that will provide you with this information. Again, this is what the if I go to the SkyX, and I click on, I say find HD 189733, it will show me the star, and it'll give me the information related to that star, right? So in the left hand corner, you can actually see that it has the object information. It has the object name that we talked about. It says the magnitude, 7.67 magnitude, and it gives me the azimuth and altitude in the horizon. So in this case, this thing was at 70 degrees altitude at that time when I was the time that I was going to be looking at this. So it tells you the rise time and the set time and the transit time. Look at this. So the transit time was at 8 o'clock at night, 2022. So that allows you to basically confirm that you'll be able to at least take a picture or take multiple images of this star in that particular day, right? So once you basically have your plan, you have to execute on the plan, of course, right? So my suggestion is that arrive early, kind of like make sure that you set up everything that you need to set up: imaging, tracking, boarding equipment, give time for your telescope to be at stable temperature. You'll see something it's called wave, and wave is related to the heat waves that actually can affect the actual image of the star that you're trying to record. For doing this, you will need a camera that is cooled. So an astronomical camera. So make sure that you give enough time to get the camera at the temperature that you want to take a picture. Have the mount ready and the computer running all the needed software. We'll talk a little bit about the software that you will need to do this, and how to set up an imaging sequence. So when I did this, I was using MaxMDL. So MaxMDL is a image acquisition software, very popular, and is relatively straightforward on what to actually, how to actually set up a sequence. You tell it the name of the object that you're going to be trying to take an image of. In this case, HD 189733, and you can see that where it says set up sequence, I have enabled, in my case, it says filter 4. That was the V filter on my filter wheel. And I want to do 5-second exposures, 250 exposures of 5 seconds with a minute in between, right? So this is going to take some time, right? Because I want to be able to see the ingress, the midpoint, and the egress of the planet. And so I set up the setup sequence. I set up the camera. You can see under the MaxMDL, you can actually see that it's at -20. That's the cooler, starting at 1, and it's been 1 by 1. It says full frame. So I'm set up. I'm basically ready to actually take take some images about this, right? So you have to find the host star with the imaging equipment. So how do you do that, right? I mean, not only that, you have to align the camera to capture the host star and comparison stars. So that has to be a very, very precise pointing of your equipment, of your telescope, to this star. So to be able to do that, SkyX has this feature is called Image Link. That basically what it does is you take an image, you take a picture of the area in the sky where you're at, and you ask it to solve the plate, which means you ask it to tell me where exactly I am looking at. Okay. This is not cheating, but it's actually makes it a little bit simpler. With the sky, you can actually do what is called a closed loop slew. And if you tell it to, I want to go to that HD 189733 star, and I say closed loop slew, it'll put it right in the middle. It'll basically take an image, solve the plate, find out how far away is that particular star, and put the actual star in the middle. But that may not be what you want to, right? I mean, you remember, you need to be able to take images of comparison stars as well, which is the reason that if you look at this image, when I did this, I was doing this with a 12-inch LX200 SCT. My camera was a ST10 XME, which is relatively a medium-sized detector for it, but it gave me a pretty nice field of view. And I took a picture and I said, okay, Image Link, tell me everything that I can actually see. Tell me where the telescope is pointing at. And I don't know if you can actually see it in your monitors, but each one of these things have a little black dot. If it has a black dot, it means that it was used as a reference to solve the plate, to find out where the telescope is pointing at. So there you are. You point to the star and you ask for the object information, and that star is the one that I was looking for, 189733. So I know once I have taken that image and solved the plate, that that star is in a location it's in my detector, and I'll be able to take images without any problems. And you notice that it's not in the middle. The reason is that I wanted to also have some comparison stars nearby. So once you have set up your telescope and you have set up the sequence and you're pointing at the correct place, you press the button that says start and you take and save all the images. In my case, remember, it was 250 images altogether. It was close to 3 hours of 3 or 4 hours worth of images. And really, I mean, what you're praying for is that there's no clouds, you know, that you don't have something that you know, come over and will ruin the you know, the images themselves between images. And again, the reason being is that you're trying to detect minute differences in relative brightness of that star, right? So what happened after that is that, you know, you took all the images and you still don't know if you did good or bad. So the first thing you do, you basically take away the electrical noise. That's what calibration. And then you align all of the images. That doesn't change any of the relative brightness in any of the images. So that doesn't change, you know, the image itself. It just aligns them once with the other. And then one of the reasons why I used MaximDL, you do a photometry analysis of the image. MaximDL actually has that. It has that feature. So as part of the MaximDL package, you can do a photometry analysis of the images. And basically what you do is you give it the image list, the list of all the images that you took. I'll point out that you can see it has a _C, which means that they have been calibrated already. So they're calibrated images, and you tell it, okay, I want to do a photometry analysis of each and every one of those images. Excuse me. So it uses the information from the header of the image. If you know what that means, it basically means that when you take an image, the camera or the software will record embedded in the image. Will record the information of the time that it actually took it, the intensity that it actually, each one of those objects actually has, the exposure, and the pixel scale that is also associated with that image. Okay, so you're doing photometry analysis with MaximDL. The output of that analysis is a spreadsheet. That should not be a surprise, because this is basically the way to record what each and every one of these images actually had in regards to the information, right? What we're looking for here is you can see that on the left-hand side of the spreadsheet, it has a time in Julian date, Julian date. So that's it, the time. It says object 1, reference 1, and then check 1, 2, 3, and 4. The object 1 is the HD 187733. So that's the relative. Sorry, that is the relative brightness of that star. Ref 1 is there's a utility that you can actually put a 0 magnitude star. It's actually it's synthetic. It's not actually zero reference star, but you can actually have one in there. So it's there. That ensures that the data is actually same. And then you can see that I've selected 4 different stars to make sure that that those, to basically compare the object in questions with them. Okay. All right. So once you do that, right? I mean, once you have that CSV file, that's a, it had data for 250 images, right? So I mean, so basically in this case, you have, those 5 columns, 250 rows, and what you do is you feed that information, that CSV file, that comma separated variable value, comma separated value file, that spreadsheet, you feed it into this program called AstroImage-J. AstroImage-J is free. It's also kind of fantastic in the sense that it calculates the air mass and other losses, things like wind, dew, clouds. If you had stuff like changes that have to do with heat, they will actually calculate those also. Compares the host star, the star that we were talking about, the 189733, to reference stars. In my case, is to reference stars. So I remember I had 4 of them, and basically do ensemble photometry as well to ensure that it actually has a same result. It adjusts the output for air mass and other losses. So what you see is actually a calibrated output of how that star actually changed throughout the time, and it plots the host star magnitude versus time, right? And in this case, I did it in absolute value as opposed to a relative value, and generates the light curve. That's the end result. That's the goal. That's what you're looking for. So the result of that, right? I mean, is this, right? People have asked me, throughout your astronomy career, I know it's a hobby, but throughout all my time that I have been in astronomy, what is the most exciting thing that you have actually ever seen? And I'm sharing that with you folks. I mean, this is, right, a planet that is actually, eclipsing that 189733. What you're seeing there is the transit of 189733b in front of that star. And you can see that you can see the air mass and losses in the bottom. These are the stuff that actually calculates. And I don't know if you remember, but we were talking that it was 8 o'clock when he was transiting, and you can actually see that number 2 in there is actually the minimum. So that was about 8 o'clock at night, and you can see it was like 1, 2, 3, 4 hours afterwards that I ended up finishing. So like from 7:30 or 7:30, maybe 7 o'clock at night, all the way through 1 o'clock in the morning. And again, lucky enough that I didn't have really too many extra losses like clouds, dew, waves, and wind that messed up the data. But you can actually see how the data becomes a little bit noisier as you actually get more and more mass, air mass associated with it. But there's no doubt, right? I mean, we actually can see that we actually had a 27 millimag dip on the actual brightness of the host star. Went from 7.67 to 7.7. Sorry, yeah, 7.60. But 0.98. So yeah, 27 millimegs. The length of the transit was 1.74 hours, and the mid transit was at 2.7 universal time. So there you go. That data. I mean, I was jumping up and down, right? I mean, this is at home. I mean, you're doing this analysis at home. You're not doing this on the field. So this data was sent to the transit search program at the University of California in Santa Cruz, and was accepted as good data, and was used by that group, and it's also part of the amateur exoplanet archive as well, and it actually made it as a valid point of reference for 189733b. So those are the results. That's basically the goal of actually what you're trying to do, and hopefully this is something that kind of gives you an idea that yes, it's very hard. You definitely needs to be lucky at to be able to actually get this data, but it can definitely be done. I actually have two of this. So the resources, again, this will be posted after the presentation in the listserv for you to use. But the NASA exoplanet site that we talked about, there is the for exoplanet search and planning. Then the Astro Image J, there's the link for that program to analyze the data once you get it. And I also included two PDFs. One is the Practical Guide to Exoplanet Observing by Dennis Conti. So if you want more information, you definitely I would recommend that you download that. Is free. And the same Exoplanet Observing for Amateurs. Bruce Gary, he was really into this in the early 2000s, and it's a little bit dated, but it actually is it's a good reference on kind of the details on how to actually do the this detection and so forth. And of course, the American Association for Variable Stars Observers, AVSO, which I 100% support. And if you want to get into this, I recommend very highly to actually get into observing and documenting the variable stars prior to getting into this into this exoplanet. So with that, any questions from the group?
Isaac, very nice presentation. Thank you.
Thank you, Michael.
Excellent presentation. Thank you very much. Well done. Very well done.
Thank
Question. Apparently you get all the information from the group. Like if you go out there and you miss this, you could have to wait years for that same one again, right?
Yeah, depending on how often the transit occurs, yeah, there might be years that basically it's predicted that it happened, and it won't come back again in years. Most of these are hot Jupiters, which means that they actually are big planets, very close to the star, and they have very, very short epochs. So basically have very the orbits are very small. So so they basically happen maybe 2 or 3 times a week. So it's not too bad. So there's a gamut of things. And the key for that, again, you can look at once you decide that you want to do this, and you make a query, you can sort by, you know, when it's going to occur, and how long is going to be, how long the transit is expected to be, and how much the actual dip is going to be. In other words, you know, what the diminution of brightness of the host star is expected to be. And again, 2%, if I'm going to do this, 2% is kind of the minimum that you want to get into.
Isaac, would you talk a little bit about your observatory and what it took to get it set up to do this?
Great question. And in fact, that is very true. In order to do this, well, first of all, I was in Hutville. Hutville is a location which is in Knox County, away from the lights, not very quiet, and you know, very relatively dark. Not as dark as JGAP though, but it is relatively dark. And the most important part is that I was very lucky. I mean, this is Ohio, and high clouds typically appear, you know, like after 2 or 3 o'clock in the morning, high clouds appear and things get ruined. I used a 12-inch LX200 OTA. It was mounted on a Paramount ME, and you know, we're talking about, yes, you know, prime type of equipment to actually do this. 12 inches is, I mean, this is a magnitude 7 star, right? So you would think, well, you know, you can actually do this with less than that, and you can. Honestly, you don't need 12 inches to actually do this, but it's definitely nice, because what happens is that you only need a few seconds, and that, you know, basically diminishes a lot the chances for something happening in between and messing up the image. So 12-inch LX200, the mount is a Paramount ME, location is out where there's no lights, no cars, no nothing, and really and luck.
Well, Isaac, since you're taking pictures for 4 hours, did you have a guide scope running also?
You know, I did not have a guide scope. Let me put it this way. I looked for a guide star, and if I didn't have one, it was really no big deal, because, you know, the images I was taking was actually very, very short images, 5-second images. So I didn't need to guide. And remember, at the end of this, once I took all the images, I actually aligned them all. So 5-second images, I know it was a few hours. The error that I had in pointing, you know, that could have been in, you know, you can actually see in 4 hours, was basically negligible. I you know, all the stars were aligned with no problem whatsoever.
And another question, how many stars have you done this for?
I did too. I retired with 100%. I have this one and another. I did too.
Okay.
It is really it's really luck. I mean, as you can see, again, planning is paramount. You know, you need to get it started, and you know, ideally you want something that will have a, you know, relatively, you know, like I said, this was 4 hours worth of data. The transit itself was about 2 or 2 3/4. So basically, you know, you need to be able to do it, so you get the best opportunity to be able to be successful.
Sounds like you almost have to do it somewhere where you do have power too, because I know a lot of the older laptops wouldn't last 4 hours.
That is true. Yes, absolutely.
Yeah.
Yeah. I'm lucky that the observatory is powered, and you're exactly right. Otherwise, you would be in trouble. Yeah, exactly right.
Yep.
And we didn't talk about the software, but again, I use the Sky, but again, any program that you can use to gather data, you know, you're fine. But you have to be, you know, very precise on being able to point the telescope to the correct place. So you need some kind of software that will be able to solve the plate. Nina, by the way, does that. Nina is free. So you know, just I want to make sure that, you know, you don't have to buy the Sky to do this. You know, there's some other programs that will do it as well.
Is this software pretty big hard drive hogs or memory hogs?
Say that again. I'm sorry, Jim.
Are the needed software when installed, does it require a lot of memory?
It doesn't. In fact, well, for operation, it doesn't need a lot of memory. For the program themselves, they usually do, because they normally have all the catalogs. So and the catalogs are huge. They're measured in gigabytes. So yeah, for the program that actually you use to find out where the things are, usually they're pretty hefty as far as memory, storage memory is you know, requirement and so forth. So it can be, you can't do. I was gonna say, can you do this on a small? Maybe. New computers are pretty powerful.
Mm-hmm. Yeah. Any other questions? Okay.
Right. Well, thank you very much, everyone. I appreciate it. I hope that you enjoyed the presentation, and have a good rest of the night.